Alright, hello and welcome to Lab 5. This one is all about trees, and I've tried to make it as fun as possible, so we're going to play tic-tac-toe in code. Okay, so the first thing we need to remember is how to encode binary trees in C++, right? Let's pretend like you got your root node, and that's a pointer, right? You have a pointer to the root of your tree. And every node looks like this. It's a struct, right? Struct node. It looks like this, and it has data. Every node contains data and pointers to its children. Okay, so int data, at least for this example, I'm holding ints as data, and then it's always node star left and right? Node star left and node star right. So those are the fields, the standard fields of a node struct. You can also maybe include a pointer to a parent. That is also sometimes a thing, like if 42 has a child. That's the left child, that's the right child. 13. Sometimes like these nodes also have pointers back up the tree to their parents, but that's not strictly necessary. So maybe this is our tree. And so this is a node that contains 42 as data, and then a pointer to this node as its left child, and a pointer to this node as its right child. Yeah? And then leafs just have null pointers to their left and rights, meaning that there is nowhere to go. You can't go left, you can't go right, things like that. Okay? So that is how you can make a binary tree. And so you can add some more nodes, make it a binary search tree if you wanted to, but that's how it works. So those are binary trees in C++, and you can definitely have more than just left and right nodes. You can have more than just a binary tree. You can have maybe 3 nodes, 4 nodes as children. You can have a whole set of children, and that's what we're going to do in this lab. Every tree is going to have not hard-coded left and right, but a complete set of children, okay? Of arbitrary size. Okay, so we're going to store a set of nodes, set of node pointers, essentially, as children. All right. Another thing that we need to remember is that a tree is represented by a pointer to its root. So if I give a pointer to the root of this tree, that is essentially the tree. That's me passing along the tree. Yeah. And then because we're cool, instead of normal pointers, we're going to use shared pointers. Okay. Just like we were using at the start of this class in our first lab. So let's talk about this lab, this particular lab. I have made a very cool artificial intelligence system. It encodes a algorithm called Minimax that plays tic-tac-toe optimally, which is really cool. I've made all of that artificial intelligence for you, but it's your job to fill in the missing pieces, okay? And the way that trees come into play are as follows. So if you consider how many ways can you play tic-tac-toe, like how many ways can you fill in a game board, you can have at most 3 to the 9 possible states. There's strictly less than that, right? Because every part of the tic-tac-toe board could be either empty, an O, or an X. So you have 3 options for 9 of each of those places to fill in. So there are somewhat less than 3 to the 9 possible game states, and that's not a whole lot. Right? So what we can do is we can make a tree of game states, a tree of tic-tac-toe boards to show how you could play the game. Okay, so let me draw an example tree for you. So here's the root of a tree that represents the way that a tic-tac-toe game, the way that any tic-tac-toe game could ever be played. So here's the root, and as children of the root, you could then, what's the next move? Let's pretend that X always goes next. You could then do this. You'd be like, okay, X could have gone here, that's another state. X could have gone here from the root state, or X could have gone here, ... There's 9 options, right? And then finally, X could have gone way down here. That's the idea. And then it's O's turn at this level, and you try a move for O. Yeah? So, okay, let's say, like, try all the possible moves for O in this tree. For this tree, for example, O could go... because we start here, O could have gone up here. That's a spot for O to go. O could have, starting from this tree, gone here. That's the next possible state. Dot, dot, dot. O could have gone all the way, starting from here, down here. Those are all the different 8 possibilities of how you could play the next move with O, right? And you could go and do this for every possible game board state in your tree, right? And then it's X's turn, you try all the possibilities for X, again, down here, and all of these things. And then eventually, you're going to get to a state where you've won the game, where somebody has won the game. So for example, if it's been played out this way, like an X is here and an O is here, maybe eventually, like X went here, O went here, and X went here, this is a leaf. This is a leaf because now the game is over. Do you see that? So you can represent, as trees, the entire game of tic-tac-toe, which is super cool, right? And naturally, you're going to have more than just 2 children. Potentially 9, potentially 0. I hope that makes enough sense. And so you have a ton of leaves that are the last board in a game state. You can't move anymore because somebody's won or all the spaces have been filled and it's a tie. Yeah. So that is the game tree. And after we build this tree, that's when my little artificial intelligence program can hook in and search for the move that, like, because you have all the options in front of you, we've made this tree, you can go and count, okay, if I choose this option and I'm X, this chance, like all of these cases, if I try and find all the leaves from this game board state, it's very likely for me to win. I win in more states than I lose, so maybe I should pick that move next. Does that make sense? That's how you can come up with an artificial intelligence program. Definitely ask me more about that if you're interested. So what we want to do is like find the move that maximizes our chance of winning and also minimizes our opponent's chance of winning, depending on your perspective. Okay, so that's the algorithm that I've implemented already for you. So let's talk about what you're going to be doing. Your job is to essentially create this game board. That's the first big step. Okay, and you are going to represent the game board as the following. Maybe we should look at the code first, but here is what the tic-tac-toe board is going to look like for you. It's going to be a vector of vectors of characters. So boop. So for example, this particular game board can be represented in code as the following vector of vectors of characters. You have a dash to mean nobody's gone there yet, an X character, an O character, and then we had an O character, an X character, empty space, nobody's gone there yet, and then it was dash X dash. So this is your game board. This is how it's going to be encoded inside of this lab. So that's it's a vector of vectors of characters. There's always exactly 9. Okay, could be the initial game board is just a bunch of dashes everywhere, and this is your board. Okay, and so what you're going to be doing is making this tree, seeing all the ways that you could move, and then my code takes over and tries to find the best move for you. Okay, so let's look at this code now. So here are the files. I think the best one to look at first is tic-tac-toe.h. And so yeah, here is the data structures that we'll be using in this lab. You have a board. This is a type def, so I can just say board instead of saying vector, a vector of characters all over the place. And then here are all the nodes that we're going to make the game tree out of. Here are our game tree nodes. Here's the type for that. Okay, every game tree node, going back to here, because every tree has a bunch of nodes in it, every game tree node holds a board, right? The current board at this level. So maybe it's this game tree node right here. It has that exact board saved. And then it also has a set of next moves, a set of game tree node pointers, right? Because those are your children, just a bunch of pointers. Potentially 9 children, potentially 0 children if you're a leaf, but it's going to be a set of game tree node pointers, and they're ordered in a special way so that I can print them in a pretty way. So don't worry too much about this comparison operator. It just makes sure that when you print something, it prints in the right order so I can grade you based on that order. Okay? Not a big deal. but it's a set of game tree node pointers, just as usual, just like you would write a pointer to your left node and a pointer to your right node. So that's how we're saving the board, and using that, we're going to build a tree. Okay, this is our game tree. It's got to have a root to the very first game tree node, that is the blank game board. Okay, and that's where we're going to build our tree. It's a pointer to the very first node in it. That's the root. Okay, and so there's a lot going on: a constructor, some public methods, some private methods, and I think we're ready to learn about them. So tic-tac-toe.cpp is where we're going to be implementing all this stuff, and I've implemented a ton of it for you. But the things that you're going to worry about are build tree, winner, and BFS. Okay, so your job is to build every possible game board and all the ways that we could get to it. Okay, so like starting from the root, pick all of the next game boards, come up with them all. Okay, so that then we can recursively build trees from those spots. Okay, that's what you'll be doing. So let's go there. Oops, I accidentally opened up the test file. There we go. So the constructor just makes the empty board to start out with as the root, not a big deal, and then we start building the tree, where X is the first person that is running. Okay, the first player is X. So that's what build tree does, and so let's talk about build tree, because that will be where you should start. Okay, so what you need to do is generate all the possible moves from a given starting board. Okay, so here's build tree. You're going to be given a game state. Initially, it's the very first move in the game, so the state is blank, and then you're going to recursively generate every possible move. Okay, so that's going to come into 2 steps. So there's always the concept of who's the current player, who's going next, and then who is, like, where am I currently trying to compute the next elements of. Okay, what's my current board to go off of? So maybe I have a blank board and it's X's turn, for example. I need to pick all the possible ways to play the game from that point onwards. Okay, so that's how it's going to look. And so you're going to have a subtree root and a player. And let me try and teach you what's going to happen there, what you need to do. So let's say player is X. So that means it's X's turn to make a move. And then here is an example subtree root. Let's say that the game board looks like this, X, O, O, X. Okay, so this is your subtree root. It's a pointer to this board. Subtree root. And then your job is to recursively call build tree from this root. Okay? Your job is to recursively build a tree from here, because you need to fill in things. You need to try all the possibilities. If it's X's turn, X needs to have the possibility of going like X, X, O, O. X should go here once. X should try to go X, X, O, O. X should then try to go here. All of those options. And you're going to recursively build out all of those options. Okay? That's what's going to happen. So the first thing you need to do is pick all of your immediate children. Figure out the next move based on your current game board. Okay? So figure out your current moves. That's the first thing you need to do. And you can just do that with generate next moves. I have made a nice helper method for us to do that. So here is how you generate the next moves. I've implemented it for you. Okay? This generates a list of all the possible next board states given a current board and the player who needs to go next. Okay? So you can just use that. You're welcome. So I'll give you the next things that you could do. And then it's your job to, for those new states, for those new boards, play the game. Create the subtree rooted there. So make a recursive call, make a recursive call. Does that make sense? So recursively build the trees for those children. Because it's a smaller sized game tree, you can use induction to prove that the recursion is going to do the right thing. It's going to be great. And then eventually it'll stop. Okay, so make shared pointer game tree nodes for each of the next moves. Those would be the children of your subtree root. You got to fill it with its children. Okay, so I walk you through how to do that, and then you need to set the next moves of your current subtree root after you do those recursive calls to your build tree helper method. Okay, that is what needs to happen. And eventually, there will be no more moves. Eventually, you'll hit the leaves. There are no more moves given by generate next moves. And so this loop will do nothing. You'll just set it to an empty set, and that will automatically make it a leaf. There's no special case for you to worry about there. It'll just work with the current loop. Okay? Not a big deal. So that's build tree. You're going to be recursively building up all of the possible ways to play the game. Okay? So that's the first thing that you'll implement. The next thing that I want you to implement is the winner method. Okay? So if you are given a board, just tell me who the winner was, if there is one. If there is no winner, return back the question mark character. Okay? So let's look at the code for that. All right. So on to the winner method. This one's super easy. You just take a board by reference and you see who the winner is. If you find that the winner is X, you return the X character. Otherwise, if it's O, return the O character. And then finally, if it's a tie, you have to return a character, so let's just make it the question mark character. That can mean tie. Okay? So for example, let's do it this way. You're given a board, and you just gotta look through it. Just try all the different ways to see if there's a winner. Like if this is what the board looks like, you have to give back the character X. Okay? Otherwise, like if it's a tie or nobody has won yet, you can't find somebody with 3 in a row, right? Then you just give back question mark. That's all. That's a very easy function to write. You just have to try all the possibilities. So it's like somebody won if they got 3 there, 3 there, 3 there, 3 there, 3 there, 3 there, or there, or there. Okay, so you got to try all these possibilities. If somebody won, give back who it was that won. Okay, it's never going to be the case that multiple people have won at once. Okay, there won't ever like be an O here or anything. I promise that. Given the way that we're building the board, that is impossible. Okay, that is the winner helper method. And then finally, the last thing that you'll implement is BFS. Technically, you don't need it to like figure out how to best play tic-tac-toe, but this is a good algorithm to get some experience with. Okay, so BFS. I want you to implement BFS through the entire game tree. So you're building this entire game tree, and you got to go through it in level order and visit all the places. So I want you to do that and give back the boards that you see in the order that you visit them. So that's essentially it. So here's your tree. Pretend that this is your game tree. Boop, boop, boop. You can have as many children as you want. Let's pretend that there's 3 children of the root, and then everybody else has 2 children, for example. And your BFS is going to visit all the boards in this level order, just like that. And so this is the first one you see, the second, the third, the fourth, the fifth, the sixth, the seventh, on and on and on and on forever. Okay, so you're going to implement that next. BFS. It is, let's see, where is it? Should be down here somewhere. Let me search for it. Oh, there it is. So yeah, you just take your game board, which is a member variable. This is one of the methods of the game tree class. What you're going to do is go through every node in the game tree, starting with the root, of course, and just make a list of all the boards that you see in level order. Okay, so perform that breadth first search using a queue and keep track of all the boards that you see. Just push them to the end of this list, for example, and that's the order in which you saw them, in that level order. And you're just going to give back that list, and I'll compare that in a test. Okay, so that's your BFS operation. And yeah, that's pretty much what you're going to be implementing. We can go and look at the write-up if you would like, but there's not much more to say, really. Okay, so yeah, get that starter code. Here are all the things. I've given you a reference file. That's what you're going to be comparing against for your breadth first search. So that's what you should see when you do the breadth first search. And then, yeah, you're just going to implement those pieces of the game tree class. Please read all this. That's how you compile and things like that. And there's some extra information there. But most of what I said is all that you need. And so the one file that you're implementing is tic-tac-toe.cpp, that class implementation. So that's the only file that you need to submit. So get that working, get the tests passing. I have this test tic-tac-toe file, and it makes sure that all of your things are working, okay? So if you run it like this with run tests, then if you run the program like this, it will run our tests. So here are the tests that I've made for you with a bunch of game trees, making sure that the game tree got built properly, that the BFS is doing the right thing. And so here are all those tests. Get those passing, and you get full credit. And once you have them passing, for fun, if you don't run the program like this, if you just say dot slash tic-tac-toe, it'll ask you for a game board and whose turn it is, either X or O, and it will tell you the best possible next move to play, given your game board. So that's a fun thing that I've implemented for you. Feel free to ask me about the algorithm if you're interested, but you don't have to worry too much about it. I've already given it to you. So your job is tic-tac-toe.cpp, do the breadth first search, figure out the winner, and implement the game tree generation. That's probably the hardest method. Okay, so please get started on that. This is a 2-week lab, so do week 16. Plenty of time. Please ask me all the questions that you have about it, and I think that's all I wanted to say. So good luck, and I will see you next week, or in the next lecture, depending on which one you're about to watch.